Hello and welcome to NPTEL MOOC. This is a course called Electromagnetic Wave Propagation in Guided and Wireless Media. The course ID of this particular course, which will be offered in the January 2019 session, is EE21. And my name is K. Pradeep Kumar and I am Associate Professor in the Department of Electrical Engineering at the Indian Institute of Technology Kanpur, and I am the instructor of this course, which, as I have told you, is Electromagnetic Wave Propagation in Guided and Wireless Media. What is this course about? Now, the title of the course of course gives you the picture of what the contents of the course could be. The main concern in this course is to study electromagnetic wave propagation in two kinds of media. One is what is called as guided media, which encompasses all those media in which physically there exist structures which help the wave to be propagated from point A to point B. Those are called as guided media. And then those media where there is no physical structure, but electromagnetic waves are still taken from point A to point B, except that we do not really call it as propagation. The correct word would have been radiation. I did not want to put both words in the same title. So, therefore, I have essentially said that it is electromagnetic wave propagation in guided and wireless media. Wireless media would essentially mean media where there are no physical structures which take electromagnetic waves from one point and to the other point. Examples of guided media in which there are physical structures which guide electromagnetic waves from point A to point B are the familiar transmission lines, the microwave waveguides, optical waveguides and optical fibers. Examples of wireless media, of course, there is no physical media as such, but you may have heard of antennas being emitting radiation, and antennas also absorbing a part of radiation where the electromagnetic waves are propagating in air or even in the deep space as such, right. And it also encompasses propagation of electromagnetic waves in the form of free space optics, meaning you have a light source and then you have a lens, and light actually propagates between the media in air or in any other kind of a media, but there is no physical structure of that. The goal of this course is to treat in some deeper context of the transmission lines, microwave and optical waveguides and optical fibers. These collectively are the guided media, and then also talk a little bit about antenna basics and free space optical wave propagation, both of which are very important, and to finally look at what is called as wireless channel modeling. So, this will be a brief topic in which we are going to study how to, we apply the ideas of propagation and radiation and then see how electromagnetic waves propagate and how do we model that in free space. And this wireless channel modeling is of course very important for wireless communications as such, right. If you look at this slide, you will see that I have put in these different guided media, all pictures taken from internet of course. So, what you can see here is that on the x axis down below is the increasing wave of frequency, and the axis on the top here, which is again along the x axis, but the corresponding numbers are in the wavelength, right. Now, we know that wavelength times frequency is given, is a constant which of course depends on the media, but in free space that value will be equal to the speed of propagation. So, if you want to obtain the corresponding wavelength or corresponding to a given frequency, all you have to do is to divide the frequency, or rather divide the speed of propagation c, which is 3 into 10 to the power 8 meter per second, by the frequency value to get the wavelength. Wavelength is measured in meters, frequency is measured in hertz, and these engineering units of kilohertz, megahertz, gigahertz, terahertz are the multipliers that we associate with the basic frequency measurement. So, you can see here on the leftmost corner where in terms of frequency we are somewhere between 30 hertz to 300 hertz is the power line cable, right. So, these cables are something that you may have seen, even you will see them in every place on earth where the electricity is kind of distributed. So, these lines are very long, they actually cover the entire country and sometimes cover cover bigger countries as of course. In continents they may actually even pass through different countries. So, these power line cables are essentially very long cables, okay, and their function is to transport energy or transmit energy from one point to another point, and they are actually transmitting the electromagnetic energy. Of course, at such low frequencies we actually talk about voltages and currents. So, therefore, we can call them as voltage transmission lines or current transmission lines or simply power line cable, because they actually transport the voltage and current, the product in some sense gives you the power, right. So, but what you have to note is that these frequencies are very low. In India they are about 50 hertz, in US and in some other parts of the world they are about 60 hertz, and the corresponding wavelength is actually very large, right, because these are in hertz, the corresponding wavelengths are in hundreds of kilometers. Okay. Moving up in the frequency axis, you will see that there is a coaxial cable which is another structure, and these coaxial cables are something that you have used in all of your laboratories, right, and you also have used these coaxial cables to connect up the dish antenna to your television sets, and these coaxial cables contain one inner conductor and one outer conductor, and they normally operate anywhere from low frequencies something around 3 kilohertz all the way up to a few megahertz, around 30 megahertz, 40 megahertz, and good quality connectors and coaxial cables may even go up to a few gigahertz frequency region. Okay. So, these are coaxial cables which we are going to study in some length in the course. Then you see a certain set of components which are grouped here. Their frequency ranges are anywhere from 30 megahertz all the way up to 3 gigahertz. Beyond that their performance deteriorates significantly, and these lines essentially consist of the same two wires just as in a power line cable or a coaxial cable, but the geometry of these lines are very different. In fact, they are not really called as lines. These microstrip lines that we talk about are most commonly found on printed circuit boards. So, if you tear open your cell phone and then break it open to see the printed circuit board that forms the body of the cell phone, you will actually see many lines running in this particular form. So, these top one which is shown with this W with a width of W is called as a trace, and then these are the variations of microstrip line. This is called a strip line, buried strip line, and then coplanar waveguides and whatever, right. So, these are mainly used in printed circuit boards, and their region of operation is typically about 30 megahertz to 3 gigahertz, right. When you increase frequency further, that is you go into tens of gigahertz, you then end up in the band which is actually called as millimeter wave band, and one of the important things that is coming up today is the millimeter wave systems which are expected to be employed by wireless networks as well. But if you want to connect electromagnetic energy or rather transport electromagnetic energy from point A to point B at these frequencies in these tens of gigahertz and hundreds of gigahertz, you have to use what are called as microwave waveguides or just waveguides, right. These are hollow tubes of different cross sections. So, for example, you can see here there is a twisted cross section or the kind of a twist that you can see, and you can see the straight waveguides with a rectangular cross section. I have not shown here, but you will also find these waveguides in the circular cross section, and pretty much any kind of a geometry which of course is determined by many other parameters can be made to work, and these microwave waveguides are essentially used to guide energy from point A to point B in the region around tens to hundreds of gigahertz. But please note that their lengths cannot be usually very large, owing to the simple fact that they become very expensive if you want to use them. Very economical and most powerful way of conveying electromagnetic energy from point A to point B at the optical frequencies, right, at very high frequencies is given by these two examples. One is called as an optical waveguide and the other one is called as an optical fiber. An optical waveguide is one which is used in many integrated optical circuits, and optical fibers of course as you know already are laid out pretty much everywhere on pretty much at every place on earth, and these optical fibers, which are very tiny strands of dielectric dielectric materials, made out of dielectric materials, can carry large amounts of information, and this information is actually in the form of electromagnetic waves which are changing with respect to time, and therefore, information is being propagated from point A to point B. And here we are really talking about distances which are like intercontinental distances, like thousands of kilometers long optical fibers, and the corresponding frequencies are of course in a few tens to hundreds of terahertz. The frequency axis is kind of logarithmically placed, therefore, the frequency increases rapidly as we go around, right. So, but I would like you to take a minute to look at this entire slide and then realize such an important point, that almost all of this guiding behavior will be given by a very few set of equations called as Maxwell's equations, and of course, we have to apply the Maxwell's equations under different approximations to describe the propagation of electromagnetic waves, but it is very surprising that from frequencies which are just a few hertz all the way up to few tens and hundreds of terahertz is actually covered by Maxwell's equations, right. So, that is the beauty of Maxwell's equations, which form the basis of studying electromagnetic waves guided by these structures. Please note that I am using the word structure, the meaning of that will become clear in the first lecture that we are going to have after this introduction video, right. And to just summarize the wireless media, you can, I know I have just picked up some pictures here. We are going to look at a few basics of antennas. This is a dish antenna that you might have seen everywhere, and these are the fields which are radiated. Note that these fields keep travelling in air, and then there will be a receiving antenna which will intercept and then convert some of that electromagnetic wave into voltages and currents, and if there is some information contained in these fields, you will also get that information in the receiving antenna. And the corresponding problem, as you increase the frequency further up and up, or the wavelength reduced to such a small extent, are the effects which are called as diffraction effects that will come up when optical waves. So, these are optical waves. The specific reason why there are these lines, we will look at it later on, and when they try to pass through an aperture, they tend to spread out, okay. And this phenomenon is called as diffraction, and we are going to look at what diffraction is and how this diffraction in fact is a fundamental component of all of these wireless channel models. So, here you have a base station tower, and then you have a cell phone, and then there are a lot of buildings, and in this particular landscape there is also a mountain, and you can see that this blue line corresponds to a light or electromagnetic wave coming straight from the base station to the cell phone, whereas the other waves are all actually diffracted, reflected, and so on, right. So, the phenomenon that we are going to study in diffraction will be directly applicable for wireless channel model, okay. So, this is in essence the course content. Briefly, we are going to start with transmission lines, and then we look at applications of transmission lines. Our focus will be to consider applications for signal integrity and to study those specific problems that come up when you try to make printed circuit boards and try to drive signals on that printed circuit boards. Then we move on to electromagnetic waves in free space. We are going to look at a few mathematical techniques of describing electromagnetic waves in free space, and then apply those techniques to study diffraction of electromagnetic waves, and then we come back to guided structures, and then we look at guided waves in metallic waveguides, those cross section microwave waveguides that I talked about, and then we extend that one to dielectric waveguides, and finally we talk a little bit about radiation. Some part of the radiation we would have already considered in the free space electromagnetic in week 3 as well. So, we are going to supplement that with week 7 of fundamentals of radiation, and finally close by talking about wireless channel modeling, right. The textbooks that I have here are just a suggested textbook. On the web page I will upload much more number of textbooks and references. The textbook that I would recommend, if you can get hold of these textbooks, is the second one, Electromagnetic Waves by David Stalin and others, and this is now available in the Indian edition as well. It pretty much covers all of the topics that I have shown here in this slide except for wireless channel modeling, which anyway I will suggest some more literature for you, and there are other references which are, some of them are very comprehensive references. We probably will not be required to look at all of them in that detail. Okay. So, the goal here, just to reiterate, is to understand electromagnetic waves and then to see these different structures which guide electromagnetic waves, and to see what are the specific problems that come up when you are going to use these structures to guide electromagnetic waves. This topic is very important, and the prerequisites for this topic is, I mean this course is that you should have had a first course in electromagnetic theory. I also have given NPTEL courses on electromagnetic theory. I would recommend strongly to study any of those, to study some of those videos, to view some of those videos, and know a little bit about Maxwell's equations and boundary conditions, at least until the start of the third week, right. So, with this let me close, and I hope that you will enjoy this course, and we will have more details to share on the website. So, please look at the website periodically for more details. Thank you very much.